Okay, so let's talk about SHM. So this is simple harmonic motion, and this is SHM, abbreviated as SHM. Let's just draw a spring, and let's just hang a mass at the end of this spring. So here you've got a mass, W equals mg. Now suppose so you got the spring and you've hanged the mass at the end. Now you've just let it hang freely and wait for some time. It is not moving anymore. Now because it's not moving, it is in equilibrium. So here, let's just draw this dotted line as the equilibrium position. Equilibrium position. Equilibrium position. All right. So you are going to pull this down. Let's just say you pull this down here, or to here, and you let it go. So what's going to happen? So you pulled it down, you let it go. It's going to oscillate, isn't it? It's going to oscillate. It's going to go up and down, up and down, up and down. Okay, so while it is moving down, it's accelerating towards the equilibrium position. Oh man, look, I smudged it. Never mind. Oh, okay. So it's moved down. It's accelerating towards the equilibrium position. As it passes through the equilibrium position, although again it's carrying on moving upwards, it's moving upwards. And again, it's being accelerating downwards. So it's going up and down, but as it passes through the equilibrium position, that's when it's the fastest speed, isn't it? The fastest speed, the fastest velocity, or the maximum velocity. So it's the maximum. And when it passes through the equilibrium position, the acceleration is equal to 0. So this is what's happening. So you've let it go, you've pulled it down, and then you let it go. It's going to go up and down. Now the amplitude is the distance between the equilibrium position to the maximum points. So from here to here is the amplitude. From there to there is also the amplitude. IMPLITUDE. Okay, so that's the amplitude. Okay, so it's moving up and down. So as it's moving down, it's accelerating towards the middle, and then here's when the speed is 0. Yeah, so speed is 0. When the speed is 0, it goes back up. It's accelerating, and then as it passes through this point, the acceleration becomes down. But remember, it's still going up, isn't it? So let's take this as positive. Let's just take that side as positive. Massive positive sign, and this is negative. So as it's going down, this is the displacement. So the displacement is negative. The acceleration is positive. It's going up. Remember, so anywhere in this region, the acceleration is always in the opposite direction to the displacement. So the acceleration is always on the other side of the equilibrium position. So anywhere the particle, or anywhere the mass is on this side, negative, the acceleration is positive. And when the mass is in this region, the positive region, the acceleration is always negative, and it's always away from the displacement. Okay, so how do we write this? So let's write this as A is equal to minus, let's say the constant of proportionality is K, and we call that X. Now, there was a bit of confusion because the A must always be the a must always be opposite to x. So in this case, this is acceleration. X is displacement. Now, how do we make the constant of proportionality always positive? Now, the reason being, if this is always positive, then if that's positive or negative, then that is always opposite to the displacement. Well, the equation is a is equal to minus omega squared x. So this is the equation for SHM. What that means is that the acceleration is proportional to the displacement because of that sign. And the acceleration is always away from the displacement. So it's always pointing in the opposite direction to the displacement. So if the particle is here and it's negative, acceleration is always positive, which is going towards that part. And if the displacement is positive, the acceleration is negative, meaning that the acceleration is towards the equilibrium position. So that is SHM. So SHM is this is the formula for SHM. Okay, we need to derive, as in that we need to get to this. So for SHM, we need to derive v squared is equal to omega squared a squared minus x squared. So that's what we need to derive from this. Okay, so in terms of displacement and velocity, what is A? Okay, so we know that A is A's acceleration, isn't it? So A is acceleration, and it is the change in velocity divided by time taken. So for GCSE or for AS level, you know that's v minus u over t. But if we write it in terms of changes, this is dv by dt. A is equal to dv by dt. dv just means change in velocity, dt is the time taken, or the change in time. Okay, so we can rearrange this as dv by dx times, now the old-fashioned way of writing times is a dot, so I'm going to do dot. So dv by dx, dot means times, dx by dt. Because what happens when you times them together, the dx cancels and you're left with dv divided by dt. And what is dv by dt? V. So we can say that A is equal to, I'm just going to swap them around, v dv by dx. Alright, so now we can rewrite A as v dv by dx is equal to minus omega squared x. Now you need to know integration here. Let's put the dx to the right hand side. So you're left with v dv equals minus omega squared x dx. So let's integrate both sides. Integrate v with respect to v is half v squared, and that is equal to, integrate this with respect to x, you have minus omega squared divided by 2x squared. Now remember, it's always have to plus a constant, and we need to work out what that constant is. Okay, so what are the boundary conditions? Boundary conditions. So if you remember, looking at this diagram, when the displacement is at the top or the bottom, so when the displacement is at the amplitude, what's the velocity? 0. Because if it's going up and down, when the displacement is at the bottom, the speed is 0. When it's at the top, it's also 0. So when x is equal to a, v is equal to 0. So that is when it's at the top or at the bottom of the motion, the speed is 0. So let's put that in there. So v is equal to 0. So the left hand side is 0, so that 0 is equal to minus omega squared over 2 x is equal to a, so you have to, so you're left with a squared plus c. So what is c then? So c is equal to omega squared over 2a squared. So we've worked out what that constant is. We're going to put this back into here. So now you're left with half v squared. That is equal to minus omega squared over 2x squared plus, because that's a plus there, omega squared over 2a squared. Oh, there are halves everywhere. Let's get rid of the halves. So this times everything by 2. So now you have v squared is equal to minus omega squared x squared plus omega squared a squared. We don't like to have a negative in the front, so let's switch them around. So now you have v squared is equal to omega squared a squared minus omega squared x squared. We can take omega squared out. So v squared is equal to omega squared a squared minus x squared. We can square root both sides. I mean, we can keep it in this form. That's fine. That's not a problem. But if you want to work out v is equal to, if we square root the whole thing, we can square root individually as long as they're multiplied together. So we can square root omega squared, and that becomes omega. And we need to square root the right hand side, this brackets. So that's a squared minus x squared.